Now I want to kind of dive into wall treatment. And wall treatment itself is important because that really sets the stage for how turbulence is generated, dissipated. So in industrial applications of turbulence models, empirical relationships, they capture this. The implementation of wall treatments, we don't want the implementation that we have to burden us. Like some people, if you implement a turbulence model, you're going to get it perfect. It's going to be accurate. And I want, in order to use this turbulence model, you have to have a y plus of 1. And we're going to talk about y plus a bit here in a moment. But that really hamstrings the person who's putting the mesh together. It's basically saying you need a really, really fine mesh everywhere. But it's going to be hard because you don't really know the flow structure around it. So you have to put a fine mesh in areas where the velocity is really large near a wall, or you can put a larger mesh in an area where the velocity is smaller near a wall. But it makes it a little tricky. But we're going to review how these models are put together in Azore in particular. And so the first thing we want to start with is this near wall shear stress. A common way of characterizing the flow structure near a wall is this y plus plot. And so where the x-axis right here is y plus, which is a ratio. It's kind of a Reynolds number per se. If you look up here, it's the density times this u tau, which is called the shear velocity. Y is your distance from the wall divided by the viscosity. So this is really kind of a wall Reynolds number, and it kind of characterizes where you are in terms of a distance from basically a wall as you progress away. And this axis over here is u plus. And u plus is another non-dimensional number, which is a ratio of the velocity away from the wall divided by this wall shear velocity, this kind of value right here. And the good news is when you have laminar flow, u plus and y plus, they like equal one another. And so it's beautiful. We have this wonderful relationship that we can use very reliably. For turbulent flow, it's not nearly that simple, but people have found that they have these logarithmic relationships like this right here that allow us to kind of characterize the flow structure out away from the wall. And so we have these two areas that allow us to kind of characterize these empirical relationships, but we kind of want to span the whole thing. And like, here's one model. You can see here, there's kind of a departure from the experimental data in this area right here. And there's, this Van Dries or Dries, I'm not sure how to pronounce that, model is one approximation of trying to capture the curvature between the two of them. Azore uses a relationship for the K omega SST model, and there's this blending function that's used between the log layer and the laminar layer. And this kind of gives us the ability to have a very precise treatment, and it results in a relationship that looks similar to this Van Dries number right here, and how the velocity varies from the wall all the way out to the bulk stream. One of the things that I kind of have characterized over here is what are the real things that we're trying to do with a wall treatment relationships that we have here. And I kind of put these 4 regions together and really kind of characterize what's important where. And so when your y plus is quite small, the molecular viscosity basically is the only thing that's important. So, and that makes a certain amount of sense because there's nothing else happening there. The turbulent, it's such a small length scale that turbulence plays no role. As you start transitioning away from the wall, the molecular viscosity becomes less important. And that happens like right around 5. But between 5 and 50, both the molecular viscosity and the Reynolds stresses. So here you can kind of see right in this area, this is where turbulence begins to impact the relationship for the viscosity in that area, or what's really happening in that boundary layer. The turbulence is beginning to play a role, and we need to account for it in some way. And then once we reach on the order of 50, we're in the outer layer, and we can go, depends on who you talk to, 30, 70, or 300, 700, something like that. And many of like the power plant models that we put together, we have models even with Y pluses even larger than this. But this is kind of what we are really trying to do with our turbulence model, is kind of leverage this algebraic relationship to characterize this shear stress. In the end, that's really what we want. The next thing we want to look at is heat transfer. And here we get to lump on even more like empirical relationships for characterizing the wall heat flux near the wall. And here things get a little trickier when you have heat transfer. Oftentimes you have properties that change, material properties that change with temperature. And so now that it makes kind of gray. When we were talking up here with these relationships, you have viscosity. If nothing's changing up here, what viscosity you use? Well, you use the viscosity, you know what it is. When you have heat transfer, all of a sudden, your viscosity is changing. And if you have a very high heat flux, that viscosity could be changing very rapidly. And which one is the appropriate one to use? Well, it may become very dependent on the mesh size that you have there as well. So Azore, there's a lot of magic, I would have to say, that and choices that are made in what to do in these approximations for this relationship here. But the fundamental math here is that we have this Y plus number. It is connected to the turbulent kinetic energy in the near neighbor cell. So this kind of provides a blending process, a non-dimensional blending process between the boundary layers, or thermal boundary layers, between those two spaces. And we also have this T star, which is another scaling value that's used in here. And that one is also a blending process, which is basically your fluid properties there. And so then the choices about how you choose those values at this location matters, and the ultimately how your Q is calculated. So that kind of characterizes, the broad picture of how, the mathematics of wall treatment is going to be performed in Azore when you have a heat transfer problem, or you're looking at skin friction, or those things. This is the mathematics. This is really what we're trying to represent. All of these variable fluid properties scale very well over large temperature ranges, so that when you do put variable fluid properties in there and you expect to see an impact because of those things, those should be realized when you put those properties into Azore.